Hey, welcome back to Introduction to Computer Networks at NTU. This is Polly again, and we are now at week 13, episode 23. All right, time flies. And guys, unfortunately, this week is going to be heavy. We have many assignments due. So PA8 is due this week. And we have 7 quizzes due. Okay, among these, 4 of them straightforward, trivial, but the others might require some logics, thinking, and common sense. Also, tomorrow, about 1 p.m., the exam 2 results will be out. Okay, so that's about what's going to happen this week. And good morning to you all again, or good afternoon to you all again. Sing, Paul, Bingwei, Stanley, Anthony, Caesar, Lopez, Louis, Pinyu, Kangshuo. Oh, Kangshuo is Ricky, James, and Sherman again. Okay, Sherman, it's okay. Hey, announcements of the exam results can be traumatic. I understand. Okay, take things easy. Lopez. Yeah. Hey, I recall that you prefer you're called Louise. Yeah. And hello, Calvin. Good. And good afternoon, Yuhan. Today, all we're going to talk about is the modern forwarding. If you recall, last week we talked about IPv4, IPv6, and we matched the destination IP address in the packet header to decide which interface to forward the packet. So it seems that the field we match is very fixed, very specific destination address, and the action, forwarding, very specific. But in modern days, using the software-defined networking routers, we do generalized forwarding. Okay, so in this video, Polly will explain again, traditional, specific, modern, generalized, and introduce a new term called flow table. As opposed to in the traditional forwarding, we call them the forwarding table, because the action is specific, just forward. And in modern forwarding, things are general, so we call it generally a flow table. Last section in chapter 4, generalized forwarding and SDN. So in these SDN routers, okay, the way we're doing forwarding is actually different from the traditional one, therefore we call it the generalized forwarding. In traditional routing, if you still recall, in the data plane, when packet arrives, we look at the destination IP address and we try to match destination IP address to the prefix entries in the forwarding table. If we match one, what we essentially do is to forward the packet to the link interface indicated in the entry. Okay. So in the traditional forwarding, what we're doing in terms of matching, very specific, the destination address. What we're doing as an action is simply to forward the packet further. But in SDN routers in the data plane, the matching and actions are now a lot more general. This is the architecture of the modern routing, or SDN-based routing. Now the separation of data plane and control plane, this part is actually very similar to the traditional routing. Now if you recall the overview of chapters 4, you should recognize in SDN, the control plane look very different. Instead of having routing algorithms running on each individual routers, we now run the routing algorithm centrally on one or maybe a couple powerful machines. And these machines could be slightly far away from the routers in the network. Now, what's a bit similar though between SDN routing and the traditional routing is this. After route computation, we generate tables like this. Okay, this is similar to traditional routing, right? In the control plane of the traditional routing algorithm finished computation generates forwarding table, and we install forwarding table to the data plane of the traditional router. Now, in SDN, tables are generated as well from the routing algorithm computation, and we also install these tables to the data plane of the SDN routers. You see, the control plane to data plane connection there between SDN and traditional routing, very similar. The only slight difference is this. In traditional routing, we call these the forwarding tables, but in SDN, we call them the flow tables. Okay, so each router there will be installed with these flow tables to handle packets coming in. And so the flow table, if we zoom in, it looks more like this in SDN. In traditional forwarding, we have what? Prefix, the first column, and the link interface, the second column. The actions being taken is very simple, matching prefix, and then forward to a link interface. So what we're doing is always forwarding in the traditional routing. But in SDN, these actions could be more general, okay? Not just forwarding. So calling it a forwarding table is a bit awkward. So instead, in SDN, we call it the flow table instead. And by flow, SDN is actually referring to each of these entries, each of these rows in the table. That is also saying if packets coming into this router, okay, where multiple of them matching a particular header combination and therefore take the same action, they belong to the same flow. So each row here is a flow. Okay, so we have a table of many flows in a sense. So what I'm showing here is also an example. Packets could come in with the headers looking like this, the destination being 0100, source IP address being 1101. Okay. Now we need to go ahead and look up the flow table in this router, okay, and then determine it should go out on interface 2, arriving at this router next. Now in order to do that, there needs to be an entry, let's say this one here, okay, matching the destination and source address. So in the header column, okay, of this entry, there should be specification looking like this. D equals 0100, S equal 1101. Therefore, when this packet arrives, look up, we match this entry and therefore take the action here. Now, forwarding to interface 2, the action there should look like this. Okay, so matching this packet to the combination of header fields and take the action. Now, in the meantime, we take the action, this thing here. Okay, for this entry, the counters, both the packet counter and the data byte counter will be added. So packet counter will be added by 1 for one packet. Data counter will be added by the size of the data here in the packet. Okay, so you see, header column here for matching purpose, last column here for action purpose, and counter here for management purpose. All right, so that's the general idea of the generalized forwarding, the modern forwarding. Next video, you'll see that it's not only just more general in ways they match and in ways we act on the packets. In fact, one can also set priority to these different flows. So in the next video, you will see that a few examples of these flows and learn a new term called open flow. That is the protocol that's defined, allowing communication between the centralized controller to the SDN routers so that one can set up these flow tables on individual SDN routers. To put in simpler words, we take a combination of these header fields with specific values and we define that as a pattern, okay, for a flow. So whenever there's a packet coming in, the SDN router is essentially determining which flow the packet belongs to, because that flow entry is going to tell the SDN router how to handle the packet. That is called the generalized forwarding. So step number 1, the most important step. For each incoming packet, take the header. Try to match the various patterns, okay, in the flow table. If there's a matching entry, go to the action column, so that's step 2, and then handle the packet that way. It could be simply to forward the packet to the next router, or drop in the packet, or modify the packet, or send the packet to the remote controller. So that is usually for debugging purpose, by the way. And step 3, increment the counter so that we track number of packets matching to the flow, number of bytes, okay, matching to the flow. Now, priority. Yeah, so this is something that we have not yet talked about, the priority column. Okay, so the flow table should have actually 4 columns instead of 3. Let me explain why we need priority there. Yeah, these patterns, okay, in the flow table. Some of these patterns could be more coarse-grained. Many of the packets might match the pattern. Some might be finer-grained. Okay, few packets will match the pattern. So if we have multiple patterns that are coarse-grained, chances actually high that they overlap. Okay, therefore, for a packet incoming, that packet could potentially match to multiple patterns, multiple entries. And each entry specifies an action. So, which actions do we take then, right? So priority there, okay, is to specify which pattern carries a higher priority and which one carries less. So we could differentiate or break the tie among all the matching patterns. Which one should be taken priority, therefore we take the action in the prioritized entry. So priority there is to disambiguate all the matching entries. Now in traditional forwarding, we don't need to specify a priority. Why? Traditional forwarding there is to do prefix matching. We do have multiple prefixes existing in the forwarding table. So one packet could actually match to multiple prefixes. Then, you know what? In traditional forwarding, we are also doing the longest prefix matching. That actually breaks the tie naturally, because there's only going to be one longest prefix. Okay? Unlike in SDN, we could have multiple patterns, and the patterns are now general, right? It's not always prefix, so you cannot use the lengths to break the tie. So we have a specific priority field there to break the tie. Okay, so the forward table in a router, 4-column, and it defines how the SDN handles a packet. It defines the match and action rules. To be more concrete, let's look into 3 examples. Now, in all 3 examples, we look at the source address and the destination address header fields. Now, in example number 1, we don't want to match the source address being 1.2. something. Okay, so the asterisk here meant wildcard, meaning arbitrary values for the last 2 octets. Destination address must match 3.4.5 for the first 3 octets, and then it doesn't matter what the 4th octet is. Now, all packets matching this pattern will be dropped. In second example, source can be anything, but destination address needs to match 3.4. something, and then we forward all those packets to interface 2. Third entry, 10.1.2.3, as long as the source IP address is exactly this, we send the packet back to the remote controller. So 3 examples, you get a rough feeling. Now, let me come back here. I have not yet explained what OpenFlow means. This is the data plane abstraction for SDN routers, all right. What does OpenFlow mean? OpenFlow, capital O, capital F. It's a very specific term. It is the protocol defined for communication between the data plane router to the control plane remote controller. So the remote controller installing forwarding table using the OpenFlow protocol. All right, so those 2 videos give you an overview of the modern forwarding. Next, more formally, let me introduce flow table. And in the meantime, let me also introduce the pop-up quiz today. Number 1 is, between the traditional forwarding and modern forwarding, which one is more specific? I hope that you were paying attention at the beginning of the lecture today. And so the next video is going to introduce more formally the flow table, and you will see exactly how many fields you can try to match and the actions you can take, and also how the counter work. With the generalized forwarding explained, now let's go back to this notion. Flow table. This is one of the most important things in SDN's data plane. Recall early slide. Flow table consists of a number of columns, and you now know it should be 4 columns to be exact. There's this column priority, and we just ignore that here as it's not often used in SDN anyway. The stats column is essentially the counter column in the early slide. There are 2 counters we know. 1 counting bytes and 1 counting packets. Action column, 4 classes of actions. One can forward a packet to an outgoing interface. One can forward a packet to the remote controller. One can drop a packet as an action. One can also change the content of the packet as an action as well. So, all these, straightforward. Now, this column here, very complex. It really depends on the header fields you're using and the values you're using. So the entries, the rule column part of the entries can be very diverse. So the rule column here, in the early slide is also called a header column. The reason it's called a header column is we're using the header fields essentially to compose these rules. In the 3 examples we just walked through, we're using the source and the destination address. These are the header fields in the network layer packet header. one can use other fields in the network layer header, okay, for the rule. One can also use fields in the transport layer header, such as the source port number, destination port number, to compose the rule. One can also use the link layer header fields to compose the rule. What's even more amusing is this. These are all fields, okay, in the packet headers. One can also use fields that's outside of the packet headers. This is called the switch port. What this means is the packets, okay, coming into the router through a particular incoming port. Okay, so that's what the switch port meant, the incoming port, the incoming interface. So how we forward the packet can also depend on where they come in from. Right? So that's also why, okay, in this slide we refrain from calling this column the header column, because we do have a field that's not necessarily a packet header. So we call them rules in general. All right. Hey guys, pop-up quiz number 2 is now on the live chat. Do you like the modern routers to be able to read? I mean, routers of course reads the IP layer header, the network layer header, because forwarding is a network layer function, right? But you see just in the video that in the flow table, these SDN routers, the modern routers, can read the transport layer header. The header's a layer higher, and the link layer header. Hey, the layer one, the header one layer lower. And how does a router reads the link layer header when it's not yet added, right? Especially at the center side. Okay, so pop-up quiz number 2 here asks, do you like SDN router reading the link layer and the transport layer header? Based on your intuition, how do you like it? All right. That might require a little bit of thinking. It's okay, take your time. And we move on to the next video. So flow table, very general. Wow, sounds powerful. You know what? It is. In the next video, you will see 4 examples, 4 different uses of the SDN routers. And you will see that it can work not only like a router, not only like a link layer switch, but also firewall, NAT, and in quiz 38, a special function that I will not disclose and you guys will need to figure out. So pay attention, quiz 38 is coming up. Let's take a look at how diverse these rules can be, again through a number of examples. First is the destination-based forwarding. Now this is essentially the traditional forwarding, where we look at the destination address. So if you have a packet, the header, the destination field says 51.6.0.8. Now we forward that packet to the output port number 6. So you see here, the SDN router can actually emulate the behavior of a traditional router. And the flow table there is actually a very general form of the forwarding table. Okay. The second and the third example are there to serve security purpose, to set up firewall entries. So let's take a look at what they're doing. First one is actually trying to match the destination port number header field. So if the packet's destination port number is 22, we drop the packet. The second one is actually matching the source address header field. If the packet source is 128.119.1.1, then we also drop the packet. So you see, dropping packet, definitely, okay, something that the firewall does. Now, why blocking packet going to port 22? Why blocking packet coming from a particular IP address? Allow me to explain. So port 22 is also the port number of the SSH server. So this is the server that you contact to every time you try to log into the workstation. So after you type in SSH, what do you do next? You give the username, right? And then the server is going to prompt you for password. The hackers around the world is trying to SSH into the machines around the world. Using what? A mean or a root username and guessing the passwords for the root or a mean. Now, if they guess the password right, then they get into the workstation and they get to play around and set things up or change things or encrypt your PA assignments and then send you ransom emails. So blocking packets to port 22 is to block any login request to port 22. Therefore, SSH is disabled, okay, on the machines behind this firewall. Second entry there. Okay, so this is actually more to try to prevent this attack, DOS attack, denial of service attack. You see, yeah, system admins around the world, especially those who are experienced, they will go up to these websites where the system admins share, okay, IP addresses of zombie machines. So if one day a hacker hacks through the workstation, okay, and take over the workstation, 140.112.42.161 is going to be a zombie IP address. Okay? So the experienced system admin, okay, after looking up the website displaying all these zombie IP addresses, can set up these entries, okay, with the zombie IPs here. That would actually block all the zombie incoming traffic if a higher level hacker comes in, okay, and asks all the zombie machines to issue, for example, login requests. Okay, then our machine is going to under attack. So experienced admin setting up these entries ahead of time will prevent us from the DOS attack. And this attack is also called the SSH brute force attack. Yeah, guessing the password by repeatedly trying, that is a brute force attack. Example number 4, destination-based layer 2 forwarding. I know we have not yet talked about the link layer protocols, aka the layer 2 protocols. So this entry here could sound a bit fuzzy to you guys. Now, so let me tell you ahead of time what the purpose of the entry is. So with this entry, the SDN router is emulating the behavior of a layer 2 switch, of a Ethernet switch. I think we've seen something like that when we're talking about the subnet, right? Within a subnet, there are these interfaces that are connected, but the connection is there through a switch, through a link layer switch, okay, or an Ethernet switch. So you see, from one machine, this network interface could have a frame passing through and coming to the link layer switch. Now, this link layer switch, we need to look at the destination address, but the link layer destination address to decide how to forward it further so that it reaches other interfaces on the same subnet. Okay, so that is the use of the switch there. So you see why. This entry here is looking at the destination address and the link layer. That is also called the MAC address. And it looks very different from the IP address. So if this packet comes in matching this link layer address, then that's forwarded to output port 3. Right? So that is the idea. All right. So SDN routers, whether you really like the way they work or not, they are certainly not strict layer 3 devices, right? So I see that Henderson says, I don't like the mechanism because it does not provide privacy in a way that a router seems to be reading information from a layer down and a layer above. Calvin also felt that this breaks the philosophy that we are actually having layers when we are defining the internet protocols at the first place. But Caesar and Paul here says they like the way SDNs are because it seems flexible and potentially one can do many things, okay, in an efficient way. All right, it's more powerful. Yeah, flexibility to some people it's power, but to some others, for example, Sam here, hey, it's others' business. Maybe the layer 2 switches should be doing the layer 2 switching instead of a layer 3 router there doing the switching. So this time, right, I see kind of split opinion, 50-50. So one sees advantages, the other see potentially burden, right? So more flexible, but that means that there's probably more time required for a packet to pass through an SDN router. Or on the other hand, being flexible, that means you might need more circuitry there to allow such flexibility. Therefore, these routers are more expensive. So once again, in the fields of engineering, it's very often that one decision is not exactly perfect. It's very often that given specific scenario, given specific workload, one would say that that's apply method 1 or that's apply method 2 for optimization to specific metrics. Okay, so sorry in a way that my pop-up quizzes are often very general, but again, they are designed such that you guys will actually think openly and tell what you think from your mind, and you see also others telling from their minds, and you try to understand each other, then you know better engineering designs. So yeah, again, this process of debating better or worse is design. For engineering systems, the designs oftentimes are geared towards specific metrics, specific scenarios. All right, good. Yeah, again, you see 50-50. Maybe slightly more of you prefer more generalized, more powerful configuration. Good. And next is quiz 38. All right. Yeah. So this one, probably won't be spending too much time explaining, maybe except a little bit of scribbling. Okay, so this is, yeah, this is quiz 38. And we have 3 machines, 1, 2, and 3. The goal is for this machine to send traffic to this server here, but through someone in the middle. So if you can see from the IP addresses, these two belong to the same organization. That's in fact NTU's IP address prefix, 140112. And someone outside of NTU is trying to connect to a server here. Okay, this year our server is 208. Yeah. And if I set up a firewall here blocking outside access, then you guys will need to what? VPN through the VPN server on campus to come in. Okay. Hey, guys, can you recognize these entries? So source destination is to the servers on campus, and source port number destination. So this was the packet coming from the client off campus to the class server. Okay, you see that this machine here, suppose it's also general and powerful, can match these 4 fields and take these actions, changing the destination address to this and changing the port number to this. All right. When this packet after these actions arrives at this machine here, this machine has an entry that matches source, destination address, source port number, destination port number, but take these actions, changing the source IP address, changing also the destination address, changing also the source port number, destination port number. And eventually what? The packet will go to this machine at this port number, and this is the port for SSH, and hey, coming to the class server. Okay, so the question asks, what do you think these 2 entries are for? Okay, so I was not asking how to generate them. What do you think they are for? I probably kind of leak the solution already. So let's go to the score space, channel W13, quiz 38. Guys, it seems very straightforward, all right? So you guys have only 1 minute to type your answer up, and let's start counting time. What these 2 entries at 2 different machines are for? right, guys. Oh, okay. I thought I already leaked the answers. I know you guys are typing things up, but hey, due to the time constraint today, so maybe Polly would just go ahead and say it again. Yeah, these entries are for the purpose of doing VPN tunneling. Okay. Oh, wait, I got an solution from Team 13. Yeah, 13 is saying the two entries are for the VPN. One tunnel traffic to the NTU VPN, and the other tunnels it back to the class server. Yeah, so in a way that supposedly we should be going from, let me go back here. So the goal is to send traffic here. But you see this guy firewall blocks traffic going directly. So we create two tunnels, one here to the VPN server and another here. And this guy is here, the middleman, helping to connect the two tunnels together and working almost like having a direct connection, okay? Bypassing the firewall, okay? So if you say that, let's go back to Discord. If you say VPN tunneling, that would be perfect. If you say firewall bypassing, that would also be perfect. Okay, so yeah, and these two entries implement bidirectional SDN-based pull forwarding to an internal server. Yeah. So very good, Caesar. There's another term for this called VPN, but it's a little bit hard to tell whether it's private or not, but definitely virtual network, a virtual direct connection. All right. Let's see. And instead of direct SSN, another one unwraps exactly. Okay. So the VPN server here. The VPN server here. The VPN server here is the one taking the packet from the client. So you see that in order to set the first entry at the top, one needs to set up this entry here. This guy here needs to call the VPN server to set up the tunnel first. And the purpose of that tunnel is exactly translating the IP destination address and IP destination port number to the IP address of the translator. Okay, and once this middle guy here sees the eventual destination, the middle guy sets up this entry. This ensures that the packet can go to the eventual destination. Okay, good. All right, so that's the purpose of these two entries. And you see that the software-defined networking routers can be done, can be used to do also VPN. All right, so let's move on to the final topic today. So in the previous video, we see that the SDN routers are powerful. They are. So in the video coming up, you will see again these functionalities: router switches, VPN. You will see also they can also work like a NAT. Okay, NAT box. NAT box is something that we talked about last week, right? To translate local IP address to global, or from global IP address back to local. So that is also something that the SDN router can do. Okay, so pay attention to this video. This is to show you the diversity, the variety of the forwarding entries one can set with the SDN routers. And towards the end of the last video today, you will see a full example, a whole network that's configured through OpenFlow to all the SDN routers there, okay, inside a network. Okay. And pay attention to that full network example as well, because quiz 39 is coming up, all right?
With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match, okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing the packets. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN, okay, is a very general machine that unifies, okay, a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. So you see here, this network, okay, is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the open flow protocol. Right? So this controller here, sometimes being also called the open flow controller. Just like the SDN routers, okay, some of them will actually call them the open flow routers. The scenario is this: let's send packets from H5 and H6 here and here, okay, from subnet 10.3 to H3 and H4, H3, H4, subnet 10.2, okay, but through a very specific route, okay, from S3 here through S1 and then reaching S2. So yeah, we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this, okay, if you want to send data from 10.3 subnet to 10.3 subnet, because this is only one hop, okay, this is the shortest path. Traditional routing does not provide you the flexibility of, manually configure a specific route. But hey, luckily we have the open flow controller. So open flow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, S2. And these entries will look like this. Okay, inside S3, the flow entry will look like this, source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now, the entry in S1, this router at the bottom, will look like this. If the ingress port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 for entry, looking like this. Ingress port being 2. Yeah, so packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. All right, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So there I got this one. On the other hand, if it's 0.4, then forwarded on interface 4, therefore reaching H4. So open flow, really nice and flexible. So something to add is just here. Traditional routing implements a routing algorithm. You know what? Yeah, the controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional routing.
All right, quiz 39. All right, so this is the same example we saw in the video. So what I'm asking here is, given the configuration you see, what way will traffic from H6 to H4 go? So let me again triple here. Okay, so this is quiz 39. Let's see, 39. All right. Where's H6? It's up here. Where's H4? H4 is down here. All right. Now, according to the flow table set up in these three SDN router A, SDN router B, SDN router C. Okay, guys, read the tables and tell me which way will the traffic go from H6 to H4. Okay, so you could say going A directly to C, or A directly, no, A through B to C. I mean, there are only two ways. Okay, so Q1 asks which way would the traffic go from H6 to H4. Q2. If we prefer H goes directly to H4, okay, to shorten the delay, how would you change the table to each of the three routers? So router A here, here, B, and here C. How would you change the table so that traffic from H6 to H4 would travel directly this way? So in a way, I'm also leaking the answer to some degree out, right? H6 to H4 is what? A through B and C. How can we reconfigure these tables so that we go this way instead? Okay, so that's Q2. All right, with that explained, let's go to the score space, channel W13, quiz 39. All right, guys, you have 4 minutes because typing the tables up might take some time. All right, good. Let's start counting time. Polly is losing the sense of which quiz is more challenging. Okay, so quiz 39 up here is more challenging for Polly. Seems straightforward for you guys. All right, so same here is saying that from H6 to H4, the traffic can go two ways, A directly to C or A, B, C. But according to the flow table we see currently, it will be A, B, C, right? And so you need to change A's action to forward to interface 4, right? I think that's what you meant. And C's will need to do also some rule change, right? The second match, the increase should be changed to interface 1 because H4 packet will be coming from interface 1 instead of interface 2. So only when these two changes are done, then the traffic will will be brought down. A directly to C and enter H4. Okay, very good. Same. And team 6, perfect. Right, from A to B to C according to the current table. And we modify the rule to send packets from H6, which is 10311 to destination 10221. So A here changes forwarding to interface 4. Okay, that actually throws the packet towards the direction of C directly, right? B, no need to change because B will not be getting packets. And C, no need to change. Hey, C, Caesar, you want to be careful because there's the matching rules look at multiple fields, including the ingress ports. Ingress ports being 1 does not match any of the rules there. The packet will not come to H4, in fact. All right? So be careful, guys. SDN router being very flexible. Did you guys see or feel that another disadvantage of something that's powerful? Because it's so flexible. There are so many ways of configuring it. And there's also the possibility of misconfiguring it will also be higher. Right? Let's see. Oh, I love Team 13's answer here. Very detailed. Okay, for Q1, H4 will go to router A first through port 3. And through port 3 to reach router B. And through port 4, reach router C. And through port 4 again to finally arrive at H4. And we modify router A such that the matching rule is 10.3 something, that's the source, and the destination being 10.2 subnet, and the action is 4 to interface 4. Yeah. Switch B, no need to change. Switch C, the same. Similarly, just like Team 1, Team 13, Luis, guys, because the matching entry there says ingress port 2, but you see that after you change router A, the ingress port will be 1 for the packets to come, right? There'll be no entries matching exactly. So they will not take action forward 3 or forward 4 at all. So guys, be careful, all right? So team 3, very well done, but modification required. Let's see which team gets it perfectly. Oh, wait, let me come back here. All possible routes. It's okay, no problem. Yeah, I think in a way that team 1 is perfectly right for Q2, and team 6 and 13 perfectly right for Q1. Let's see if we have anyone being perfectly right for both. Oh, interesting. Interesting. You see team 9 here says H6 going through A, B, C to H4. And router A here changes the entry for destination 10.2 forward to 4. Yeah, that's how you gear the traffic through the AC link. And router C here needs to say that destination 10.2.1, which is H4, through interface 4. And you see the entries in router C in Team 9's case is removing the ingress matching part of the rule. And you know what? That will work. So removing the ingress part of the matching rule is also saying that no matter whether the packet is coming from ingress 1 or 2, as long as they're going to 10.2 subnet, 10.2.2 subnet, it will go through interface 4. So router C here, Team 9's case is actually very general. I think it's perfect, right? Yeah, I think it's perfect because 2.2.2 subnet is only in interface 4, right? No matter what traffic comes from, as long as it's going to 10.2.2.2 subnet, right? You don't need to care whether it's coming from ingress 1 or 2. Okay, good. Perfect. All right. Good. I guess you guys get the idea. Configuring individual routers from the central controller here in the middle. So there's a central controller here. So modern routing, modern forwarding is done this way. Calculation done here. And from this router, configuring router A, configuring router B, and configuring router C. And so the policy can be very flexible, just like each of you, each of the teams might have your set of rules. Some consider ingress, some don't consider ingress ports. Good. And you know what, guys? That's all the time we have already. And we just finished talking about the modern forwarding. Starting tomorrow, we'll start talking about routing, the other function of the network layer. Okay, and we've already finished talking about the forwarding one, that is chapter 4, and we will be starting chapter 5 tomorrow. Good, and I'll see you tomorrow, 10 a.m. Okay, well, exactly 10:20. Okay, bye. To be exact, should be 10:20. Right. Okay, bye, guys. And many quizzes alert tomorrow. Yeah, we just have a whole bunch of quizzes tomorrow because routing is a subject that is hard to describe. After you hearing people describing how it works, you are only more sure that you pick these routing algorithms up yourself by exercising. So tomorrow we have many quizzes to work on. All right, good. Bye. Oh, also, if you don't follow tomorrow, then this Saturday when you're working on the quiz assignments, you might have trouble doing them. Yeah. So maybe for tomorrow, show up or make sure that one of the teammates will be there. Okay, good. Bye. Yeah, there are 5 quizzes. And some of the quizzes come in 2 parts. All right, guys? Very good. Host 5 will not be affected. Very good, Team 2. All right. Okay, bye.